Q to be 1, it becomes the electric field. Let us do some more examples of calculating electric field in this lecture. I will do 2 examples here, and both are important and will be used in the future. I am going to calculate electric field due to example 1, an electric dipole, and 2, due to a surface charge. In example 2, you will also learn a trick to deal with such cases. In both the cases, we will be doing some limiting processes. So, this is quite an instructive and important lecture. To calculate the field due to a dipole, I am going to be more specific, a point dipole. What we are going to do is take the dipole to be made up of 2 charges, minus q and plus q, separated by distance 2a, so that the magnitude of dipole moment is given by 2qa, and the direction of dipole moment is from negative to positive charge. So, P is going to have a direction from negative to positive charge. If I take the dipole to be sitting at the origin and in the z direction, then I will take the charges minus q at minus a, at z equals minus a, and plus q to be sitting at z equals plus a. And I can write the dipole moment P of this to be equal to 2qa in the z direction. To make it a point dipole, finally what we are going to do is take limit a going to 0 and q going to infinity, such that product qa remains finite and is equal to some p value. That makes it a point dipole. So, let us calculate the field due to this point dipole. I am going to make it again. This is my point dipole, plus q sitting here, minus q sitting here. So, the field at some vector r is going to be 1 over 4 pi epsilon 0 q, the positive charge gives me the field q r minus a in the z direction. I will write a cube here and the vector r minus a z on the top. That is the field due to the positive charge, and that due to negative charge is going to be minus q r plus a z over r plus a z cubed. To make it more explicit, let me draw this point r. This is vector r minus a z, and the one from the bottom here is r plus a z. And we want to calculate this field and finally take the limit q times a going to a finite number. Since we are already assuming that we are going to take the limit a going to 0, I can expand these 2 quantities in the denominator. So, let us write modulus of r plus a z. I am going to include minus also right here, which is going to be square root of r square plus a square plus 2 a r dot product of r unit vector with z unit vector, which is going to be cosine theta raised to 1/2, and for the minus sign it will be minus here. Since I am going to take a going to 0, so a is much less than r, we are going to neglect a square term and keep only this term. So by binomial theorem I can approximate this as r 1 plus or minus 2 a by r cosine theta raised to 1/2, which is, thus we can write r plus or minus az cubed as r cubed 1 plus or minus 2a over r cosine theta raised to 3/2, which by binomial theorem is r cubed 1 plus or minus 3 a over r cos theta. And therefore, the field due to this dipole sitting at the origin at a distance r is going to be given as ER equals q over 4 pi epsilon 0. Inside I have vector r minus a z divided by r cubed 1 minus 3a over r cos theta minus, let me use a different color, r plus az over r cubed 1 plus 3a over r cosine of theta bracket closed. Again I am going to use binomial theorem and take the factors encircled in purple to the numerator and write this whole thing as ER equals q over 4 pi epsilon 0, r cubed I am going to take out, r cubed, and inside I am left with r minus az times 1 plus 3a over r cosine of theta minus r plus az times 1 minus 3a over r cosine of theta. I will again expand this, keeping terms only up to first order in A, and what I get is ER is equal to q over 4 pi epsilon 0 r cubed r plus 3a over r vector cosine of theta minus az minus r plus 3a over r vector cosine of theta, this blue one is the second term, minus az. Let me check if I am doing it correctly. Yes, this is indeed correct. And now if I use the fact that r vector divided by r is unit vector r, then I can write E r as q over 4 pi epsilon 0 r cubed, and by the way here this term cancels. Inside I get 6a r unit vector cosine of theta minus 2a z, which I can write as, take 2a out, 2a q over 4 pi epsilon 0 3 cosine of theta r unit vector minus z. I now want to be more general and realize that P vector is equal to 2aq z, and therefore the term 2aq combined with the first term here is 2aq times 3 cosine of theta r. Cosine theta is nothing but z dot r unit vector. So I can write this as equal to 2aq z dot r times unit vector r multiplied by 3, which is nothing but 3p dot r. Similarly, 2aq z, this whole term combined with z is nothing but p. And remember, I am taking the limit that I am working under is that a goes to 0 and q goes to infinity, such that qa goes to p, 2qa goes to p. So combining all this, I can write ER as P dot R with a 3 here minus P over 4 pi epsilon 0 r cubed. This is the expression for a dipole sitting with any orientation now at the origin, right, because now I am taking the dot product, so it does not really matter. Dot product gives me that cosine theta already. If the dipole is at, let us say, r prime, some point r prime, then this r would represent the distance from that point, and I am going to have E at r is going to be 3 p dot unit vector in the direction of r minus r prime, unit vector in that direction, unit vector r minus r prime minus p divided by 4 pi epsilon 0 r minus r prime cubed, which explicitly I can also write as 3 p dot vector r minus r prime multiplied by vector r minus r prime. Since I have multiplied by the vectors, I will divide by r minus r prime raised to 5 minus p over r minus r prime cubed. Of course, there is a 1 over 4 pi epsilon 0 outside. Next example I want to take will use Gauss's law. And in this, I want to take a positively charged sphere superimpose it on a negatively charged sphere and calculate the field due to the superposition of these two in this region where they overlap. In a way, you can think electrically this overlap region also to have no charge density. Rho is 0 because positive and negative charges cancel. Equivalently, you can also think of this as being hollow, because electrically it does not matter. So in a way, we are also calculating the electric field in a hollow region. This is hollow region when charge outside on one side is positive and charge on the other side is negative. These two centers are displaced by some distance a. I am finally going to take the limit in this case where these two charges will overlap for most of the regions. So that this negative side will give me a very thin slice of negative charge, positive side will give me a very thin slice of positive charge, and you can see in the middle the charges are going to have largest magnitude and it diminishes as you go to the side, and this region is hollow. By taking appropriate limits, limit a going to 0 and this charge density rho going to infinity, so that the charge on the surface remains finite, I will get the electric field due to a surface charge distribution rho theta or sigma theta, which is some constant times cosine of theta, and you will see that. So again I am going to use a limiting process. So let us take a sphere with uniform charge density rho r, and this problem you have solved in your 12th grade. If you apply Gauss's law and calculate the field inside at a distance r, this field comes out to be rho r by 3 epsilon naught. But let us do it explicitly anyway. So E dot ds gives me charge enclosed divided by epsilon 0. So if I take this surface, inner surface, E dot ds is going to be E at r times 4 pi r square, and charge enclosed is 4 pi by 3 rho r cubed divided by epsilon 0 here. 4 pi cancels, this r square cancels and gives me a single r, and therefore field at r comes out to be rho, magnitude of field at r comes out to be rho r over 3 epsilon 0. If I write the vector field v E at r, its direction is radially out, and using spherical polar coordinates I can write this as rho vector r divided by 3 epsilon 0. This is the field. Now let us superimpose these two charges that we were talking about. Here is the positive charge, here is the negative charge. Positive charge at this distance r gives me a field which is going like this, radially out. If I look at the negative charge, it gives me a field like this towards the center because it's a negative charge at any point. So let me make this picture again. Let me take any point. Let us say point out here. Here is electric field due to positive charge, and here is electric field due to negative charge. If I call this vector r1 and call this vector from the point where I am calculating the electric field towards the center r2, then the electric field at this point is equal to sum due to the field due to the positive charge plus that due to the negative charge. So I am going to write this as rho r1 divided by 3 epsilon 0, and since r2 is already in the direction where in the direction of the electric field, I can write this as plus rho r2 over 3 epsilon 0. Combine them together, I can take rho over 3 epsilon 0 out. I have r1 plus r2. This is r1 vector, this is r2 vector. So their sum is this vector. Whose magnitude, the distance between the centers of these spheres, and vector is from positive charge towards the negative charge. So, I can write this as rho vector A over 3 epsilon 0. This is a very interesting result, because now you look at this contribution of the two fields. If I take this negative charge here and the positive charge here, in this hollow region, field is the same everywhere. It's pointing from negative to positive side. Its magnitude is rho A divided by 3 epsilon 0, provided these two densities are the same. That is how everything worked out. And its direction is from the center of the positive charge towards the center of the negative charge. This is a very interesting result. No matter what you do, field inside is constant in this hollow region. Now, we are going to use this fact to derive field due to a surface charge distribution. Let me now take these spheres to be overlapping over most of the regions, and they are displaced by small vector A. These are the centers. Let us now take how much is the charge in this region. Now, since I am going to use spherical polar coordinates, it will be useful if I make this arrangement in the vertical direction. Right? This is the center of the two spheres. Because the distance between them is very small, I can take almost a common center, and I want to calculate the charge in this volume. Remember, how much is the volume element? This small volume element dV is going to be, again, A is very, very small. A is much less than the radius of the spheres. A in fact will tend to 0. So, I can write this as r square d cosine of theta, because this angle is theta, d phi times dr, where dr is this distance along the radial direction. So, again I am taking this particular volume element, this distance is dr. How much is dr? Remember what we said? We said these are displaced by distance a. So, this distance here is a, this distance here is a, and this is dr, this angle is theta. So, you can see that dr is a cosine of theta. So, I can write this small volume element as r square d cosine of theta d phi times a cosine of theta. And therefore, the charge in this region dq is going to be rho, the density, cosine of theta, let me bring a also here, times r square d cosine theta d phi. Recall from one of our previous lectures, this is nothing but the area element in the radial direction for this sphere. So, this is nothing but a rho cosine of theta ds. So, what I have the situation now, if I think of this as single sphere, I have positive charge here, which is rho a cosine of theta ds, which I can write as the surface charge density sigma times ds, where sigma depends on theta and sigma theta is equal to some rho a cosine of theta. In the limit of a going to 0 and rho going to infinity, such that rho a goes to some sigma 0, I can write sigma theta as sigma 0 cosine of theta. But these are two displaced spheres. So, what will the field look like? Field will be in the direction of displacement from positive to negative side. And therefore, the electric field, which remember earlier we derived to be rho A over 3 epsilon 0, is going to be rho A is in the minus z direction divided by 3 epsilon 0. But rho A, we have said, is nothing but sigma naught. So, this is sigma naught over 3 epsilon 0 z in the minus z direction. What do we conclude? We conclude that if I have a sphere over which sigma depends on the angle from some axis, if you go away by an angle theta, if sigma theta is sigma 0 cosine of theta, so that is positive all over here and negative on the other side, maximum being along this axis and then it diminishes and becomes 0 here, then E field is constant inside, as is given by sigma naught over 3 epsilon 0 pointing from positive to negative side. That is a very important result. You also learned in this how to use Gauss's theorem with two charge distributions, and it gives you a result that for a particular surface charge density you get a constant field inside this sphere.